Thank you. I'm glad I'm here this year instead of doing it remotely. This is really a presentation about Optima. Optima is a workbench I've developed for doing optimization. And I'm going to go through a simple example in Optima. There are no slides involved in this. And try to give you a very quick sense of some of the capabilities in Optima. You're looking at a screen which has 4 quadrants representing 4 different toolkits within Optima for modeling BPMN processes, simulating processes, analyzing processes and the outcomes of either simulation or generated by enactment engines, and optimization techniques for comparing different scenarios. So I'm going to start off with loading a simple model. And I'm just going to switch to a view which lets you look at the model. And it's not important to understand that it is a typical loan origination model with loans requests coming in and being processed. So the first thing I'm going to do in this model is say, okay, we have a model, we have information about the characteristics of the tasks, we have information about an expected work to be done, and we want to determine how many of the different types of resources we need in order to process in an efficient manner. And so there's a special algorithm to do an initial resource allocation based upon those characteristics. And of course, there are a lot of variations in this, but I'm just going to demonstrate a little bit of it. So in the Optimize toolkit, we're being asked a question, very simple question to make choices about this allocation. And I'm going to make a choice where my objective is, I don't really want work items to be sitting at tasks and not being worked on because there were no resources available that could perform the tasks, the performance requirements of the task. So I'm going to choose something which is going to allocate a lot of resources, but we're not going to spend any time waiting for resources. So I won't explain the way this algorithm works, but it actually predicts what the workload is in any time period and looks at the resource schedules and comes up with a schedule which is consistent to satisfy the requirement we're not going to wait. So it's completed that, and I'm just going to shift our focus over to the analytics toolkit for a second. And take the thumbnails. There are thumbnails generated for every chart that I look at, which I can then preserve and access at any time during my work in trying to optimize things. So drag this over, and it's just a typical end-to-end cycle time chart with the dotted vertical line indicating what the average end-to-end cycle time is. So you can see it's a little bit more than an hour. So we could study the way we're using resources, but since I started at the very beginning being very generous, I know that I'm probably spending much too much money on resources. So I'm going to explore this issue by using a specialized smart tool. There's several smart tools. Their objective is, the analytics in toto are very complicated. There are a lot of analytics. But to solve a specific problem, I don't need most of them. So these smart tools are fast because they take advantage of that fact. So I'm going to go to the scenario next, which is the name I provided by default to the combination of the model, the arrival patterns, the resource allocations, and the results. It's all bundled up in the scenario next. And I'm going to look at next and say, okay, what I want to work on is allocating resources. I'm going to use that smart tool to do this. So it's telling me that, the algorithm can certainly do something to help, and it's going to show us the current situation. And in the current situation, we have circumstances where we've been looking at a week, and you see patterns of utilization of resources each day of the week. I can focus in on a subset of this. I'm not going to spend my time doing that. One of the things that's important is that the per arrival cost, that is for each loan application that comes in, I'm spending $40.80 processing it, and it's telling me I'm using a total of 48 resources. So that's the current situation. Of course, we're getting the loans processed very quickly, but we're spending a lot of money to do that. So if I go ahead and run the reallocation, the idleness reduction algorithm, it's going to now, having run through all of this, says we can still reduce resources, but let's take a look at what we have. That's not supposed to happen. And so now we have a chart which depicts resource utilization and tells us that our per arrival cost has dropped to $14.10. So we have accomplished something, but we have some issues with what that looks like. I'll just take a look at it again. I'll point out the issues. The average end-to-end cycle time has gone up to about 5 hours now. In addition, if we look at the histogram, we see some outliers. You probably can't see it in the back of the room, but around 20 hours, there are some loan applications that took 20 hours because they didn't get finished at the end of the day, and they sat around until the next day. And there's even an outlier at 67 hours because applications that came in late on Friday did not get done, and they were not processed until Monday. So that might be objectionable, or it might not. It's really you know, a business decision about what's important. But what I'm going to do here is, when you learn how to read these idle charts, your eyes can tell you very quickly what to do. And what I'm going to do is I'm going ahead and actually add one more resource to the disbursement operation and run it and see what that does. So now I'm not using an algorithm, I'm using my eyes. One of the purposes of visualizing things well is that your brain can do some pretty amazing things. So I'm getting a new result. And in this new result, we've reduced the per arrival cost a little bit more, $13.60, but our end-to-end cycle time has dropped now to between 2 and 3 hours, and we have no outliers. So we have no loans ending up not getting done, loan applications not getting done by the end of the day. So let's assume we're happy with this, but we want to now investigate in this solution what things we could do to improve the process. And we have a special tool for doing that. But what I want to do is say, OK, we were only working with minimal analytics. I'm going to transfer all this data into the Analyze toolkit so that we can keep working on it. So and it's making up names. We can change these names. I don't want to spend time changing the names. OK, so now we have two scenarios. The one that we started with, that we got out of the initial resource allocation, and then what we got as a result of doing this resource optimization. I'm going to actually take the KPI chart from the last solution and put it in here. And now I'm going to say, look, there are a lot of ways we can spend money to try to improve this. How do we make choices? So I have a tool that looks at return on investment and compares different proposed solutions to see which ones give me the best bang for the buck. Which ways of spending my money have the best outcome in terms of my business objectives? So I'm going to use another smart tool that's designed for doing this. It's called Smart Productivity. And it's a sophisticated tool, but the interface is pure spreadsheets. The idea in this is these are business analysts, don't have to know how to build models. They don't have to know anything about BPMN, but they can use this tool to answer the question about how they should spend money. So I'm going to put this in position here. You'll see that there's a spreadsheet that's partly filled in with these just default values for an initial investment and ongoing costs per quarter. But we have complete control over that. So I'm going to look at strategies. I'm going to explain these very quickly. Basically, one thing we could do is do more training on the staff, maybe cross-train staff, or we may just spend the effort to make them really good at what they have to do. That's going to cost us some money, and so we're going to put down a factor which represents our estimate of the percentage improvement and a cost associated with that. Another thing we can do is look at the tasks that are being performed and say, well, you know, if we used a double monitor, that would really improve the situation. Or if we improved the algorithms that are being used for the tasks, that would improve the situation. So, well, there are a lot of tasks, and we can apply this logic individually, or we can use critical path analysis to determine those tasks that are on the critical path and creating most of the problem. So we can do any of those things. We can also say, I actually want to change the model. I want to have a 2B model, which is different than what I'm working on. It's going to be achieving the same business objective, but it's going to be structured differently. So literally, the BPMN model is going to be different. So you can do any kind of change you want to in this comparison. Also, we can take into consideration the fact that we're going to do this evaluation over time. The growth patterns may change. So I might expect we're going to conduct an advertising campaign. We're going to get more loan applications coming in for premium policies. You have to take all of those things into consideration. So that's it's kind of a little subset of what you can do there. There's also an investment plan, which is where these numbers came in the spreadsheet about the initial investment and so forth. These can be set to whatever you want to. You can decide what the time period is, over how many periods you want to do this evaluation. Those are all under your control. So I'm going to run this analysis now, and I didn't show you the revenues and costs. The revenues and costs are a way of attributing to the execution of the model the value you're getting out of it. Like, how many of the loan applications did you actually approve? Because if you didn't improve them, you're not going to get anything out of it. So the benefits, the cost, the profits are all things that you can specify in terms of what happens in the execution of all of these applications. So I'll just show it to you now. You can't see these details, but there are complicated expressions you can use, or it can be very simple. What's happened is we ran the simulation, and it turned out after 4 quarters that we never made up the money. We made an investment. We got 87% of the investment back after a year, taking into consideration interest rates and so forth. So that's not a good strategy in that situation. We can look at this, and we can try to break down exactly what went wrong. We can look at the 4th quarter and do a detailed cost-benefit analysis for the 4th quarter. And we can see the effect that our strategy had on improving the handling time for the tasks. But if we look at the costs and benefits, we'll see, okay, the staff cost went down. That was good. The infrastructure cost went down. But as a result of the changes we made, there were significantly higher penalties. There were some higher revenues, but the total effect of it is not a sufficient gain to pay for the investment. So yeah, we improved things, but we spent a lot of money to do it, and we didn't get that money back after a year. So, okay, so Optima has a lot of algorithms like this for doing things, for improving and for judging the value of improvements. It was originally conceived of in the framework of processes with maps, as in BPMN 2.0 maps. The question was, how do you take all of this analytics apparatus and optimization algorithms and make them work in situations where you don't have maps, or where the maps are, like case management sub-maps, which are not complete maps and they're assembled on the fly and so forth. So the question is, how could Optima be extended to deal with that situation? So what's been done after studying a lot of the statistics on history is to say, I can look at those statistics and I can actually, from those statistics, construct all the analytic information that's in Optima. So there are choices about, well, what format are the histories represented in? I had really two choices. There was BPath, which is a standard that the WFMC worked on that I was involved with. And there was XES, which is a format that's being used extensively by a lot of the process mining companies. I think product Disco was demonstrated here last year that uses XES. I made the decision that I wanted to be able to freely interplay with that type of a product, so I chose XES. Now, I chose XES, but the normal way in which you use XES actually loses a lot of information, and that information is then not really accessible in a tool like Disco for doing process improvement. It kind of points you in the areas which are more important, but it doesn't tell you enough of the story. So I'm going to show you a two-way connection. First of all, I'm just going to go and go to this XES section and generate an XES log. So that means from any scenario that I have in Optima, I can go ahead and generate an XES file that you can load into Disco or one of the other tools that works with that. So now we're going to go the other way. And the other way, all I need is a collection of histories. I can have 2,000 histories from some real system. Maybe that real system has a lot of agile capabilities in it. Maybe there never existed process maps for it in the first place. So I'm going to go and, so again, the idea here, just because I didn't say it before, there are models, there are scenarios. Scenarios consist of model information about simulation and the results either from an enactment engine or a simulator. I'm going to load in that XES file as if it's a scenario, because it's going to convert it into a scenario in Optima. So it's analyzing, in this case, 500 histories, and it is going to first figure out from that analysis the model, BPMN 2.0 model, that has the characteristics that if you run that model, it's going to generate statistically equivalent histories. So it's go ahead and it's figured out the model. It wants to know the name to save it. I'm going to save it. There's one there already. I'm going to replace that. Now it's constructing all of the other Optima analytics, which is used in the algorithms that you just saw. And it's now, say it's got a new scenario. I want it to save that scenario. And it's finishing up its work. After the scenario exists, I can start Optima, load that scenario in, and continue working with it with all the optimization tools. So I'm waiting for it to finish its work. Let's see what can go wrong in a demo. Okay. So it's now done, and I just want to show you the model it built. It built this model entirely from the history information. And I want to take the end-to-end cycle time from this model and put it in this pane here so I can work with it. So I have a model. The kind of things that you would see in Disco would use flow counts, and they would represent them by line thicknesses. But this is giving me all the flow counts for the 500 different histories that were in the set. One of the things that's interesting is Optima links up the different types of visualizations together. So if I go ahead and I'm going to change my view here for the histogram into another form, which is called a scatter plot. And in the scatter plot, it's showing me the number of applications that were discarded because the information was, they were rejected because the information was complete. The number of applications which were complete, but we decided on the basis of some rule that they should be rejected. And the number of applications where we actually dispersed money. So now if I go ahead and draw a box around some dots here, in any of these areas or any combination, it knows what they are, and it automatically changes all the counts in the diagram to show me for that collection what happened. And you can see all of them had one path, which is the one of rejected because the incoming information is complete. So there are a lot of ways of filtering this. End states are an important part of the modeling methodology in BPMN. I could choose the different end states and immediately see what the paths were relevant. I'm going to do one other thing, which I think is interesting, which is enable a pattern analyzer to study all the different paths. And I don't normally have that on all the time because it's computationally expensive. But I'm going to get it here, and I'm going to put it in one of my panes and show it. And this is basically says there are 5 different patterns, and it's telling me the number of histories in each pattern. For instance, there's a pattern with only 22 in it. Well, if I go ahead and click on it, what will happen is it will immediately change the diagram up above to reflect what the path looked like for those 22 characteristics. I could take a look at the next one, which has 120, and look at that, and that's all the ones where we rejected the loan. And then there are 3 others, which all look like they have the same pattern but different counts, but the reason is that there's a subpage, which we haven't been looking at, and that subpage is actually different for these 3, depending upon the way in which the loans were dispersed. So that gives you an idea of the connections that we get out of this and how we make use of the whole history processing apparatus. There's one last thing that I want to show you, which is there are some gateways in here, and the question is, well, what would the rules use at those gateways? So I'm going to pick one of these, and before I do this, I'm going to reload the simulator with some information. Okay, so looking at our counts and going, now we have all 500 that we're talking about, and looking at the gateway preceding rejecting or making a disbursement to an account. And I'm going to look at the rule. Now, keep in mind, this didn't come out of a model that somebody put a rule in. This came out of the histories. And we look at it, and we see that there are a number of different ways in which gateways can work in Optima, and the one that's being selected here is called using conditions, which means conditions on the outgoing gates. And what it's discovered is that there is a rule based upon the value of the credit record, which has determined what happens. And it turns out that whenever a loan got a credit score that was greater than or equal to 550, it did a disbursement. When it was less, it didn't. So it discovered a correlation between a property of the loan and what happened at that gateway and made up a rule. On the other hand, if we go ahead and look at this other gateway and do the same thing, we'll discover that the criteria is it just says use weights. So this is statistical. It's just assigned 95% to one gate and 5% to the other, and that's a simple rendition of the counts that are in the model. So that's giving you an idea of what's going on. My idea about process discovery is a rather extensive view of how do I create something which I can then use in the tool to do all of the optimization work. And to do that, I've had to extend XES by a number of conventions that deal with capturing additional information that allows me to distinguish between the different kinds of gateways, to have boundary events, and so forth. So all of those things can be reconstructed. And I have just a PowerPoint that I'm going to bring up here, which is intended to just go through them very quickly. This is the example that we were actually looking at. And this is the example showing the additional pattern recognition table and the correlations there. But here's some other models. These are this is a hierarchical models with a traditional top level and a lot of submodels, and it's reconstructed all of those. And here's just things using boundary events as in the structure that have been discovered in the analysis. And here's one of an example that Bruce Silver made up early on in the development of Optima, showing interrupting and non-interrupting boundary events and so forth. Here's something which involves multiple pools communicating using message flow. I've introduced a convention for showing how you can do that without drawing lines across the pools, which could, in principle be on separate pages, so that drawing message flow lines directly is not possible without some intermediate thing. And that's it.